My name is Hardy Gieske. I teach at the Lawrenceville School in the math department. And the clips you're going to see here are of a calculus project that I ran in 2009 and 2010. So let me set the scene here. We've got a group of students who were assigned this project of designing a navigational buoy. And it's basically an engineering project where they have to design something that will float that has to meet certain constraints and parameters. And they spend about 2 weeks as a big group figuring out how to do that, how to calculate all the numbers that need calculating. And then they spend about 2 more weeks in small groups, 2 or 3 at a time, and they design their own buoys. And then in the culmination, they present those designs to their peers and some guest faculty, and field questions, scrutiny, and criticism. And they have to be prepared to think on their feet, not just sort of have something to turn in. And so these clips that come will show you a couple of different scenarios about what those presentations can look like, and what it looks like when a kid is feeling the heat, or when the kid has made a mistake, or when they're thinking very well on their feet and fielding questions that they couldn't have anticipated.
Now, can you take me through, and you did a volume calculation, so that's the volume of, that if you submerge the whole thing, that would be the volume number that you would get for the whole buoy. Mm-hmm. And you did a, obviously it's done in a piecewise fashion. Yeah. And then you did a surface area calculation. Can you explain to me why you used the formulas you did for volume and surface area calculations?
Well, this one here? Yeah, that one.
Yeah, why did you use that, and why did you use, then there's one for surface area later, but earlier actually.
I guess that's the integral that we determined would measure the volume, because you could have like no uniform way of finding the volume, like, you know, shapes that are familiar, like circles or something, you can find the volume pretty easily. Or not circles, but like cylinders, but not everything is just a perfect cylinder, or it's like a perfect semicircle, so you have to use its equation form to, and then with an integral.
So why is the function being squared and multiplied by pi?
Because it's kind of, it's like, I'm trying to explain this. If we like broke it up into like infinitesimally small disks, it's just like adding up.
Breaking what picture up?
If we're breaking up one of the sections. So if we think about just breaking this into infinitesimally small disks, and then just finding the I guess in that case it would be the volume that would hold, and then adding them all together using like an integral. But it's kind of just, yeah.
So what would the disk look like for that little bottom pointy
part? It would look like just something like this, kind of. My drawing's not very good. I'm trying to do my best.
She's the designated drawer.
Yeah. She drew all those great pictures.
So I think that's, is that what
yeah, and then you could do radius is f of x.
You can put it outside the picture.
Oh, I see. So f of x is representing what about that disk?
It's representing the radius.
Ah, so when you square it and multiply by pi?
Yeah, then it will find the volume.
What does pi times the radius squared give you?
Area, I mean, sorry.
In what area would that be?
The area of this, it's the area of this disk, but then by using the integral we add them all together, so it kind of makes the volume. Because it's kind of like, the width is so, I don't know, it's like almost theoretically not there. I'm having trouble trying to explain this, but it's like if we added up all the surface areas of this flat surface together, it would give us the total volume.
Yeah.
Yeah.
There's one dimension on your picture that's missing. Can you put it on there?
Yeah.
dx.
D of x.
The second clip is a little bit less exciting for them because another faculty in the room actually found a mistake in their work, and you'll see their anxiety mount, and you'll also hear a few other students asking the same sorts of questions and wondering where the missing piece is. And it's funny because the girl who's asking about it really doesn't want to be asking about it, because she's basically putting her peers' work in a bad light, so she's sort of hesitant to do so. But it's a good moment anyway, and the kids learn why it's so important to scrutinize their work before they present. In this case, they were allowed to fix it and hand it in, completed and repaired.
I'm curious about this. You guys have 1, 2, 3, 4 different sections there.
Yeah.
And you said that you have found the central mass of each by using that formula.
Yeah.
Okay. So let's say the central mass, grab the red pen
Yeah.
and put the central mass some point there on the top cover.
I have to go and do it.
No, right there. Just where is the central mass?
Right here? Or
I
right here on the top
don't know.
cover?
You tell me.
Right. Oh.
And of the whole buoy or?
No. For each individual part.
Okay, so for this part, it's like a row.
It's not gonna work. You need to use the pen.
It's
Put
not
it in
gonna work?
slideshow mode.
Why not?
Slideshow mode. Yeah. And then the pen
Like
thing is at
this.
the bottom of the corner.
PowerPoint.
It's a PowerPoint.
They're not really like,
You can write on it.
Yeah.
so.
Go ahead.
So for this part is right there, this part is around.
Wait, don't tell them that the center mass is on the edge.
Okay.
It's on the edge.
It's in the middle.
So put Duncan, just put a dot in the middle of,
Okay.
of that. Yeah, right there, right there.
There we go.
A little bigger. Okay, and another dot on the other one, and so forth.
Yeah.
And the last one. So, how are we going to find the central mass of the whole figure when we collapse those things and put them together?
By the moment. Use the moments and then you.
It's kind of like finding like because the integral. We're trying to explain this. Do you know explain this? Right.
Let's go to the page first.
What's the page?
Getting there.
There.
One more. Two more.
There we are. Yeah. So.
We did mass over moments again.
Oh, let me see.
So and this time we just used the center masses that we'd already found by using that equation we found earlier for each individual piece and divided by the total mass for each moment.
So that's 6 contributions.
Yeah.
Well, that
Because
includes
you have to
also
account for the
the
anchor
top
chain.
disc, like the manhole cover on top of our buoy is 1, and then the superstructure is a point mass, and the anchor chain is another point mass. So that's the 2,000. That's the superstructure.
And the 6 is the distance
Yes.
Yeah, 6 is the
The
distance
distance from the base.
from the base.
Yes.
So all of the distances are distances from the base, I'm assuming?
Yes.
Yes.
Okay.
Where's the
The
whole
disc.
cover?
Yeah.
Yeah.
I think it's that one.
No,
But
why
didn't you
would
have
it-
4 pieces?
No,
Yeah, she
it's in
does.
the- it would be in 6.
But
Where's
isn't
it
it
in the
off
packet?
the disc?
Just
Well,
leave it out of this.
I thought that was one of their pieces.
There's 4 pieces.
I guess the disc is missing. Oh.
Well, you have it. I think you have it. I think it's just,
Is it your
the
disc
one
on
at
one of your
5.5?
pieces?
5.5 is one of the pieces.
Yeah, no, I really wasn't that.
Why would they do that?
The last clip here is of an entirely different group, and the students are being asked a question from a teacher who's more interested in biology and environmental science than he is in the physics and the mathematics. And so he brings a question to the table that there's no way this group could have anticipated. And the students are really asked to think on their feet right in the middle of the presentation. And it's a relaxed atmosphere. It's not that he's trying to put pressure on them, but he just has an interesting question. And when somebody like that asks a question like that, you get sort of a fuzzy boundary to the project. It's not just how does the math work or what is the physics involved. It's more about introducing another perspective to the presentation, and I think it reflects a sort of real life interaction that you might have with your own studies, that you always have to be considering what somebody who doesn't understand what you're doing will ask, or what can they add to your understanding, and you have to be prepared to think in those terms off the cuff. And I think that you get to see that kids are pretty good at it, and they get to show their versatility.
I have an unrelated question.
Go, we're done with that.
Buoyancy calculations. So I wanted to ask you a question about that. You were calculating volume of the water displaced in one of those slides. Can you click on that one?
Well, yeah.
Volume of the water displaced. And then I didn't see where you calculated the mass of the water displaced. Is that? Can you tell me just a little bit about that? Or do you need to calculate the mass of water displaced?
In terms of seeing if it floats.
Right. Yeah. In terms of seeing if it floats.
Is that where you guys were saying you missed the calculation?
Yeah. To see if it floated or not, we just use the basic principle that density is equal to mass over volume. So the entire mass of the entire buoy and divided by the density of the water displaced would give us the density of the actual buoy. And we were given the density of the water. And so the density of the buoy is less than the density of the water when it floats.
And so the density of the water is in seawater.
Yes, 65.55.
Okay, so 65.55 pounds per cubic foot. So here's what I was interested in. Would your buoy work in a lake? It's freshwater.
Depends what the density of the water is.
What number on the screen changes?
What number on it? So that's basically my question. Like, let's say you wanted to, instead of using your buoy out in the ocean, you wanted to move it into a lake. Would it still work? And if you wanted to figure out whether it would work or not, what number? Yeah, what number on the screen changes, and how does it affect your calculations?
This number would change. This whole thing would stay the same, and that number would we would still be comparing it to 50.314 pounds per cubic foot.
So if that, and how much would that number have to change for your buoy to sink?
It'd have to be
a little over 50.
What percentage, or about what percentage? I mean, do you have some idea what the relative density is of seawater and freshwater is what I'm getting at?
No idea.
That's why we have the biologist. Do you know?
It's about 1.1, something like that. I mean, for like probably 35 parts per. I'm guessing it's just. I don't know where you got that number for seawater, but I'm guessing it's like seawater varies. Sometimes you have salty.
Right.
The saltier the water, the denser the water.
Yeah.
If you've ever been in the Dead Sea and you swim in it, you like float up like a cork because it's really, really salty. Let's just assume for a minute it was 1.1. Then you just change that by freshwater is going to be less dense than seawater by a factor of about 1.1. Would your buoy still float? So just do the math. Just do the math for me real quick to show me that rather than just saying no, can you do the math for me? Just show 1.1.
I got you. Hold on. Answer. Try this.
So it's going to be less dense by a factor of about 1.1.
65.
That's more dense.
That's false. Yeah, it would still flow.
So what's the density?
You're subtracting that, and it would be about.
Oh, so you're subtracting that piece.
Yeah.
Subtract the 0.1 piece. So your buoy would still float. You could probably divide by 1.1.
Is that the same?
What?
Go ahead.
Is that 10%?
Is that the same? I don't think that's the same as.
Can you divide by 1.1 now?
I'm just curious if you get the same number if you divide by 1.1. I don't think you get exactly the same number.
Taking 10% off is different than dividing by 110%.
You want to multiply by 0.9.
So you still float though.
When I look back at the presentations and I actually think about having made this short clip for you guys, I'm very proud of the kids that I've worked with. This is the first time I did this, and this is the first time they've done this, and I think that they, first of all, gave me their full effort, which was really exciting. And I think they bought into the idea of how valuable an experience like this can be, because it will, I think every time they look at a buoy from now on, they'll think of calculus class, or every time they go to present something later, this is probably one of their formative experiences in that way, using PowerPoint and fielding questions that they can't anticipate. And I think there's a lot more going on here than just studying calculus, and I think they really bought into that.